Hi everybody, I am Pablo Peñil. I'm going to present the current status of the project that wants to detect periodic gamma ray emissions in blazars using Fermi-LAT. The members of the group of this project are Alberto Dominguez, Sara Pusson, Marco Agnello, and Stefan Larsen. About the 10% of the GGNs have jets, and when these jets point out towards our line of sight, they also call blazars. Blazars in general present high variability in the entire electromagnetic spectrum. And this variety can cover different time scales, for long-term variations that can be measured in years or months, and some variations that can last the days, hours, or even minutes. And in some of this variability present or has associated pattern, and then we call it periodicity. And why it's so important to understand or to detect this periodicity, because it can provide information about the nature and the structure of these blazars. In order to face to detect this periodicity, we develop a methodology that the sketch is showing in the slide. We started from gamma ray sources, specifically blazars, and then their emissions are observed with Fermi-LAT. That things since Fermi-LAT monitors the sky, we can have periodic measurements of these objects, and then all these observations are analyzed in a pipeline in a systematic way in order to search periodicity. And this periodicity is in terms of long term, trying to detect the periodicity with time units in years. As initial, the initial results of this project were presented in the paper Peñil in 2020, and we, starting we using blazars coming from different Fermi-LAT catalogs, and then we use the telescope time for August 2008 till September 2017. And as for the reduction, in order to obtain the life course, we use flux interrogate over 1 Jeff, and we use 20 days binning, because this bin is okay for try to detect periodicity in years. And then in order to we use different methods that can be found in the literature. Specifically, we use 10 methods in order to detect periodicity. And we complement this method with 4 techniques in order to obtain the significance of the potential periods that this periodicity detection method provide. And all this was organized in a pipeline that can be, and you can show in the slide, in different stages, in order to try to manage all the objects we have. So results of this first work that we obtain 11 high significant candidates, and in our context, high significant means that in 4 methods we obtain 4 Fox sigmas for the period we obtain, and 9 of these these detections were new objects, so new candidates to have periodicity. And we define another second group, that they call low significant candidates that they are, according to the constraint that we impose, that in 3 methods we obtain 4 sigma detection, and 9 of these 13 objects were new detection, new candidates for periodicity. So we obtained 6 of 10 were previously reported in the literature, and in 5 cases we obtained the same period, but for 6, 5, 0, 7, 16 we got a different one. The literature reports around 1 year, and we obtained around 2.7 years of periodicity. So we come back to this sample of candidate periodicity. They are composed of 24 objects. We obtain a new life course with new data coming from Fermi-LAT. We use telescope time between August 2008 till December 2020. So it's taking 3 years of our, of our life course, and a total of 12 years. As a rate reduction, we use flux integrated over, in this case, 100 meg, in order to reduce the number of upper limits we have. Because in the previous work we have a lot, and with this new property, we reduce the number of them. And again, we use 20 days of beginning for the life course. And also we improve the pipeline, introducing new methods. Specifically, we use full width half maximum in order to provide the uncertainties of the periods provided by different methods. We also include introduction models that provides more robust results, since they are mathematical background. And especially we use ARIMA and ARFIM analysis, and you can see an example of the plot we obtain. So this is the result of fitting the light curve with one of these models, and the residuals of between the light curve and the model, and then apply the autocorrelation function. We obtain this plot, and here we can observe a hint of periodicity. And then in order to start to infer more properties of our candidates and try to obtain the first evidence of the potential origin of their emissions, we use two different approaches. So the first is power spectral density, in order to fit this thing into a power law, and the value of the slope of this power law can give us some information, intense information, specifically the impact of the noise on the light course. So for that we use the power spectrum response method that was presented in ATLI 2002, and the range of values we obtain is between 0.8 till 1.3. That is values that can be found in the literature. And also we analyze the life course, fitting the Black distribution to log normal or normal distribution. And for that we use two different methods: Shapiro-Wilk test and maximum likelihood estimate. And the result we obtain is all of them are log normal fitting, as is supported by literature. These results. So this is we obtain in this new analysis six plazas with a period detection over 5 sigma. Here we have 3 of them, PG53, OBJ014, and PKS 02008. And here in the previous work we obtained for them 4, 3.5, and 3 respectively. And then on the left, you can see green vertical line that denote the highest state of the emission of these objects. And for more detailed analysis or study of PG 1553, you can see the presentation of Stefan Larsson that was presented previously to this presentation. And the second group are these 6 blasters are PKS 0454, 650716, and PKS 2155. And again, with 650716, we obtain the same period that we obtained in the previous work. So we enforce the result. And as curiosity as well, we obtain for them in this work 2.5, 2.5, and 3 sigma respectively, with the same period value. And here in the table you can see the properties of these 6 candidates. Apart from for this object, we obtain 12 additional one that have hints of periodicity of the initial 24 candidates we analyze. We remove 6 of them because they don't in this new analysis they don't we don't obtain significant detection for the periodicity. So now we have our sample is composed by 18 objects. So another thing we implement is predict the future in order to infer the behavior of the object. Is another that and this study can help to optimize and to design the strategy to observe these objects with Cherenkov telescopes, and also in order to try to solve the controversy about this detection, because some of the works in the literature assume that their behavior is compatible with red noise, and this red noise is stochastic and not predictable, and we want to with this prediction, and if these predictions are right, we want to solve this situation. And as interpretation for the periodicity, you can have several models of in the literature, and they can organize in two groups. The first one is focused that in the AGN they are a single supermassive black hole, and the periodicity can be understood for some behaviors in the jet. For instance, like house effect in the jets, or in the second scenario, for instance, motion is coming from the accretion disk that is transmitted to the jet, and depending also different shape of different structure of the jet, the combination of this both scenario generates this oscillation, this variability, and this one you can see this model of jets in the picture, and you can see coming from the work of Mohan and Mangala. And the other group model is understanding this variability in a binary supermassive black hole. And most of the works that are published are focused on trying to understand the periodicity of PG 1553. And here we have two examples. One coming from Cavaliere, that you have a main black hole with the jet, and a secondary black hole perturbate this jet orbiting around the main one. And another model presented by Tabani, we have two black holes, but they have their own jet, and they perturbate between all the system, both jets. And we observe in this case the jet of the secondary black hole. So this is a few examples of the models you can find in the literature. And in order to try to improve this knowledge about the origin of the periodicity, we want to extend our study with a multi-wavelength analysis, covering different energy bands, especially for optical to radio, and try to find periodicity and implement some cross-correlation studies that, according to different models, you can obtain the first evidence of how this periodicity can produce. And also using spectroscopy, we want to analyze different emission lines in order to evaluate the hypothesis of a binary system as generator of this periodicity. So especially observing H Balmer lines and H alpha magnesium 2, we can detect some offsets and specific line shapes generated by a secondary black hole perturbating the first one. So as conclusions, we find 6 places with a variety of 5 sigma. We also find a hint of periodicity in the 12 blazars, and we estimate the behavior of them. And according to our studies, during this year, 2021, 15 of them will have or high state or low state. So this prediction can be evaluated this year. And we also complement our study with multi-wavelength and with spectroscopy in order to improve or try to get the first evidences that provide them to understand the origin of the periodicity we detect in gamma ray. So thank you very much, and if you have some questions, you can send them to my personal email. Thank you very much. Bye.